Section 6.8 is a continuation of applications of exponential functions. So section 6.8, we're going to talk about exponential growth and decay models. We're going to talk about Newton's law of cooling. He had quite a few laws. He's a pretty important guy. And then we're also going to talk about logistic growth and decay, which surprisingly doesn't actually have a logarithm in it. So let's talk about uninhibited growth and decay. So many natural phenomena follow the law that an amount A varies with time according to the function A of t equals A naught, where A naught is the original amount, e to the kt, where k is a constant and t stands for time. Okay? A naught is the original amount when time is 0. So if we have a k greater than 0, we have uninhibited growth, right? It's just going to keep going and going and going and going exponentially. If we have k less than 0, we have uninhibited decay. It's going to keep approaching 0, but never actually hitting 0. So one thing that can be modeled with exponential growth is the growth of cells, such as bacteria, or cancer cells. I think in class I talked about kombucha. So a model that gives the number n of cells in a culture after time t has passed is n of t equals n naught, where n naught is the initial number of cells, and k is a positive constant that represents the growth rate of cells. It's a positive constant because the cells are growing, they aren't dying. So let's say I have a colony of bacteria. So much fun. We're going to pretend it's like the good bacteria, like the good tummy probiotic bacteria. So I have a colony of bacteria that grows according to the law of uninhibited growth. That's modeled by the function n of t equals 100 times e to the 0.045 t, where n is measured in grams and t is measured in days. So let's determine the initial amount of bacteria. Well, that's when t is 0, so n of 0 equals 100 times e to the 0.045 times 0. Well, that just gives me 100 times e to the 0, which is 1, so I have 100. The growth rate of the bacteria is 0.045, that's our k constant, or 4.5%. And we got all of that from the equation, which will be given to us. So if I wanted to go ahead and graph this function using a graphing utility, such as Desmos, I would see that when t, right, is 0, my n of t, or y, my dependent variable, is 100. So here's what our function would look like if we were to graph it. Now, what if I wanted to know what the population was after 5 days, where t is time measured in days, so that's good, right? You got to be some of the homework is a little tricky. They'll give you like how many days, but then t is measured in hours, so you have to multiply the days by 24. You know how to do that. You're a smart bunch. But let's say t is measured in days, and I want to know what our population is. So I'm going to take n of 5, right? I'm substituting in 5. That is 100 e to the 0.045 times 5, and that gives me about 125.2 grams, right? Remember that my function n is measured in grams. Now, what if I wanted to know how long it would take for my population to reach 140 grams? Okay, I want to know, when does n of t equal 140? And I'm going to solve this by setting 140 equal to my function and solving for t. I'm actually going to do that up here because it takes quite a few steps. So if I have my n of t equals 140, I could say 140 equals 100 e to the 0.045 times t, where t is my time. I'm trying to figure out how many days it will take for my population to reach 140 grams. So the first thing I'm going to do is divide both sides by 100. That gives me 1.4 equals e to the 0.045t. Now, this is an exponential function. In order to get this exponent to not be an exponent anymore, right, I'm going to have to take the natural log of both sides. What this does is that allows me to move my exponent to the front. So I have the natural log of 1.4 equals 0.045t natural log of e. Well, friendly reminder, the natural log of e is 1. That's one of our logarithm rules. So I have natural log of 1.4 equals 0.045t. I then decide to divide, because that's what I have to do, both sides by 0.045, and I get that t equals, if I was to plug this into a calculator, about, so we'll use these little squiggly equal signs, 7.5 days. So we're working backwards, and I'm going to have to take the natural log of both sides. That's going to be a theme of today, is to remember to take the natural log of both sides. Let's work through another example. So, this is the same example, but now it's saying, okay, what is the doubling time of my population? So if I start out at n of 0 with a population of 100 grams, what I want to know is how long does it take for me to get 200 grams, right? How long does it take for my population to double? So now I have 200 equals 100 e to the 0.045 t. I go ahead and divide both sides by 100. So I get 2 equals e to the 0.045 t, and then you guessed it, we have to take the natural log of both sides. So I have the natural log of 2 equals 0.045 t natural log of e, which cancels. So I have because the natural log of e is 1. So I have the natural log of 2 equals 0.045 t. I then can go ahead and divide both sides by 0.045. So I get t is about 15.4 days when I plug this bad boy into my calculator. Next, let's do an example that involves decay. One example of a natural phenomenon that uses decay is radioactive decay. So let's say that traces of wood burned along with an ancient stone tools in an archaeological dig site in Chile were found to contain approximately 0.167 of the original amount of carbon-14. Now, carbon-14 is I'm pretty sure it's a radioactive particle, and its half-life is 5,600 years. So if I only have 0.0167 of the original left, I want to know when was the tree cut and burned. So a friendly reminder that all radioactive substances have half-life, okay? This is the required for half the radioactive substances to decay. Medicines also, like prescription medications, also have half-lives, just so you know. That's why they have expiration dates. So I want to find when was the tree cut and burned. So I know it's going to follow the form a of t equals a sub naught e to the kt, and this time k is going to be a negative because we're looking at decay. A naught is the original amount of carbon, okay? I don't know how long it took to get to 0.017, but I do know how long it takes to get to our half-life. So if I have 1/2 A naught, so the original amount of carbon is A naught e to the k t, I know that I have 1/2 the amount of carbon in 5,600 years. That's a really long time. Now I can solve for k. So if I divide both sides by A naught, I have 1/2 equals e to the 5,600 k. I take the natural log of both sides, right? That means the natural log of 1/2 equals 5,600 k natural log of e, but that's just 1, so it goes away. And I go ahead and divide both sides by 5,600. That's going to give me k equals negative 0.000124. Okay, that's a really tiny k value. But now that I have my k, I can solve for when I have 0.0167 of the original amount of carbon-14. So I have 0.0167 A naught times A naught times e to the negative 0.000124 t. So I go ahead and I divide both sides by A naught. I get 0.0167 equals e to the negative 0.000124 t. I take the natural log of both sides, right? That gives me the natural log of 0.0167 equals, I move this to the front, the natural log of e is 1, so it goes away, negative 0.000124 t. I divide both sides by negative 0.000124. And I get that t is about 33,003 years. That's a really long time. For the remaining examples in this worksheet, I did go ahead and leave the answers in there so you can check your answers. It's missing equal signs right now. I don't know why it's doing that. But if you look at the PowerPoint PDF that I've posted, all the correct equal signs should be there.